Welcome to Palm Conference and Seminar 2018. We are about to begin our first session, which is on measuring and aligning subwoofers, and the speaker for this session is Mr. Rahul Samuel. Mr. Rahul Samuel is an award-winning live sound engineer with a global work experience of over 13 years. He has the privilege of working as an FOH, monitor, and system engineer with the best artists and equipment available in the audio industry. Based out of Dubai, Rahul is now a technical support specialist with Meyer Sound Laboratories, Inc. I would like to invite Mr. Rahul Samuel on stage.
Good afternoon, everyone. Can you hear me clearly there? Yeah, we're a small room. You want to come up, people at the back, so that we're closer. If you feel like, if it's fine otherwise. So I'm Rahul Samuel. I'm a technical support specialist with Meyer Sound for Middle East. Check. Yeah. Technical support specialist with Meyer Sound for Middle East, Africa, and India. I'm based out of Dubai. Today we're going to get into, we're going to talk about measuring audio and probably on how to use this information to align loudspeaker systems. Why do we need to analyze audio systems? Do we really need to measure these systems? We have our senses, we have our 5 senses, and these do a really good job of telling us what our environment and our surroundings are doing. And one of the senses that we in this business use a lot is the sense of hearing. Now, how good are we at hearing? How good are we at telling what we're hearing? Do you all agree that we can hear well? We have to, otherwise we probably wouldn't have been in this room. Yeah, we all can hear well. But how well do you think can we hear? These senses that we have, these 5 senses, are really good at telling us what's happening around us in relation to another level, to another reference. For example, temperature. When we all walk out of this hall, we know it's a little warm, just a little warm. And when we walk back into the air conditioning, we know it's cold. But can you actually tell what the exact temperature is outside? Can you specify an absolute value by just feeling temperature that, oh, okay, it's 24 degrees inside or it's 35 degrees outside? No. What do we use to do that? We use a thermometer to do that. What about SPL, sound level? Can we actually just hear something and tell that, okay, this is 97.5 SPL? Probably not. Yeah, but we can always reference. We can tell that something is louder than something. We can tell, okay, this is softer than what I heard last. We can do that, but we cannot do absolute values. What about delay time? No, we can't tell time, but we can tell relative time to something if the offset is large. Yeah, so if you have a speaker that's far away and you have another loudspeaker that's a little closer to you, you can probably tell that they're reaching you at 2 different times. But you cannot really tell them up close. What about frequencies? You can ballpark. Okay, low frequencies. Oh yeah, if you can just, yeah, they need to see the screen. So can you tell frequencies? You can ballpark. You can say, okay, somewhere between 200 and 500 or 1K and 3K and things like that. What about people with perfect pitch? Do you think they can tell frequencies? Yeah. They can tell pitch, which is a complex wave. They can tell you, okay, this is A node, or this is G, or this is C, and again, they can tell you relative, but they cannot tell you absolute value. What about phase? Yeah, we can hear the result of what phase is doing, but we don't know what that phase relationship is. Yeah, we know when 2 signals are 180 degrees out of phase, what happens? They cancel out. Yeah, so what about voltage and current? Has anyone tried telling about the voltages by going and touching the electrical wires? No, we always use meters, voltmeters and ammeters to do that. Yes, so now we've established the fact that we need tools to make accurate, reliable, absolute measurements. Now, when it comes to audio, this is a term that's thrown around a lot. This is a tool that we use a lot, an FFT analyzer. FFT stands for Fast Fourier Transform, and this was the discovery of a French mathematician. He's a mathematician. This is a mathematical formula that was not written specifically for audio, but it was written as an algorithm that can convert signal into the information of amplitude, frequency, and most importantly, phase. Now, I'm not going to really get into FFT, but I'm going to show you how to apply it and what to look for on the screen and things like that, because that's a full day's or probably 3 days session that we can do on that. Now, how did it all start? We had the oscilloscope or the oscillogram. This showed you amplitude information on the vertical axis versus time information on the horizontal axis. And this is a window time. So you set a window of a certain time and you see amplitude information in that. The other way you can see information is amplitude versus frequency, which is what we see in RTAs, real-time analyzers. They show us frequency information in the vertical axis, amplitude information in the vertical axis, and frequency information in the horizontal axis. Now, let's break this down. If this was a window for an oscilloscope, and we set this window to be 10 milliseconds, and in that I'm seeing one cycle, one amplitude, one complete cycle of a sine wave. I can derive that if one cycle is 10 milliseconds, that means this is a 100 hertz frequency. That's the period for 100 hertz. Now, I can see the same information in a different form, which is my spectrum analyzer or my RTA, where it is showing me that at 100 hertz, I'm seeing a certain amplitude. Correct? We'll do the same exercise again. Let's say the same 10 millisecond window, but now instead of one complete cycle, I'm going to see 10 cycles. That means I have a period of 1 millisecond, which is 1 kilohertz. And I can see that same information in the spectrum window, where I can see 1 kilohertz frequency at a certain amplitude. So this is essentially what your RTA window is showing you. What an RTA is not is an FFT analyzer. What you cannot see in an RTA is polarity. You're seeing amplitude. There is amplitude. Compared to 0, it's going either in the positive or negative, but you don't know whether it's going in the positive or negative. You cannot see phase information, and you don't know if the information that you're seeing is direct sound or is reflected sound. Now, let's look at some examples of a band spectrum. This is typically what we see in an RTA, right? This is pink noise. So in the vertical axis, amplitude, as we already established, and the horizontal axis, we can see frequency. This is a third octave band spectrum, which is what we very commonly use when we do RTAs. This is pink noise, and what defines pink noise? Pink noise is equal energy per octave averaged over time. Averaged over time is very important. If we see the same thing in a higher resolution now, this is 1 by 48th octave, or 48 points per octave. It's the same pink noise, but you're seeing it at a much higher resolution. And these small variances are that average in time that I spoke about earlier when we were defining pink noise. Now, if you look at white noise, you're going to see this in your spectrum. Why do we see a rise? Because white noise is equal energy per frequency averaged over time. So which is why we're seeing more energy here, because the octaves are much wider than the octaves that are here, which are much lower. And the same information again in a 48th octave. Classic rock would look like something like this. Speech would look something. This is probably male speech. Yeah, this is male speech. It would look like this. Electronic music would look like this. We're seeing a very wide range of frequencies. So there's energy in a very wide spectrum, and it's more or less closer to zero than some of the others that we saw. And this could very closely resemble pink noise, right? Now, how do you know that the RTA information you're seeing is pink noise or not? There's no way of telling. Unless you're actually hearing it, you don't know, because the RTA doesn't know. It cannot tell you that information. And this is also constantly changing. Now, we can do a single channel analysis, which is what will give you a result similar to an RTA. A single channel analysis is not FFT. It is RTA. So let's say we have a system like this. We have signal going into a processor, into a speaker, and I put a microphone in the room. I'm taking these measurements, and I'm doing an FFT here. This FFT is giving me this result, which is again spectrum. Can you see a bump here? This is at around, I can't see it anymore. I think that should be around 3.5K. But we don't know where that's coming from. That could be because of the source itself, where there is more energy in that. It could be an EQ that's in the processor, which is adding 3.5K. It could be the loudspeaker's frequency response. It could be the speaker room interaction, or it could be just noise. Some machine buzzing away near the microphone that you're measuring. So an RTA doesn't really tell you what's happening inside. It is just showing you energy. And that energy could be from anywhere. It could be from you breathing next to the microphone, but there's no way of telling that. So this is where transfer function comes into play. And what transfer function is doing is it's taking an FFT input channel, which some of us know as reference, some of you who've used analyzers, and there is an FFT output, which is what some of us know as measured signal. It's doing a sort of a mathematical division of these two. It's not plain division. I'm just using the word division to make it simpler. And it's giving us a result. So we have an analyzer, which is a SIM3 here. I have a SIM3 here. At the end of this, we'll try to do one round of taking these measurements. So I'm going to take my input, which is a signal from the console, so I know what my source is. Now I've set my reference. I'm going to take one from the output of the processor, and I'm going to measure it. And a transfer function is going to compare these two signals and give us certain readings. FFT input, I'm seeing flat. Remember, this was pink noise. It looked very close to this. I'm going to do an FFT output, which is signal coming out of the... Do they look close? Similar? Yeah? They're identical because I don't see any processing in that. So what the transfer function is going to do is divide this by this and give us amplitude response, phase response, and impulse response, which is showing us the time offset between the FFT input and the FFT output. So in this case, amplitude response, flat, because these two signals are identical in energy. Phase response, flat, because these two signals are identical in terms of phase. Impulse response, I don't know if you can see from that distance, I can't, but this snaps at 0. That means there is no, you can see from there? Yeah, so that means there is no time delay happening inside the processor. Whatever is going in is coming out. Good. Now, let's do the same thing with the loudspeaker now. Yeah, we'll do an FFT in, do an FFT out, which is coming out of the microphone. We see this, FFT input. This is exactly what we saw in coming out of the processor, correct? This was going into the loudspeaker, which is still flat. Can you see this side of the screen, or is it getting chopped off? Yeah, so this is flat again. But what's happening here? Why do we see this? This is the measurement of the microphone. Why do we see this? Why does it not look like this? Yeah, because it's a microphone and it's picking, excuse me, it's picking acoustical energy coming out of the loudspeaker, plus other things happening in the room. Now, if I do a transfer function, this is what I see. I see an amplitude response. What the FFT is doing, it knows what went into the speaker, correct? And now it is telling us that what is coming out of the speaker is this difference. That means something has happened to make this look like this. But this is fine. This is a good loudspeaker response. It doesn't vary much. You'll see those little bumps here and there. That's because of because of the way the speaker behaves, the room behaves, the microphone behaves. And then we have a phase response, which is actually great here, because you see your first, they're pretty much linear, and you see your first wrap down here in the lower frequencies. And impulse response. We see a time offset of, can you see it from there? 4 milliseconds? Yeah, 4-ish milliseconds. That means this microphone is receiving the signal 4 milliseconds after the processor. So this could be propagation delay. That is, the microphone is about 4 feet from the loudspeaker. So it's taking that much time to travel. Now, here again, we're able to see what the loudspeaker is doing, but we're not able to see what the system as a whole is doing. So we're lacking some data that we need in order to make a decision on the system itself. Let's look at amplitude response. We already know this. If you have two identical, if you have input FFT and output FFT identical, you get flat. If you have identical again, it's still flat. Yeah? So this line, this response that you're seeing here has nothing to do with this. This may be sloped. But if this is also sloped in an identical way, you will get a flat frequency response. What a transfer function is only telling you is changes that you've made in between this and this. Now, what do we see? Yeah, there is a change. And this is a processor. That means I've most probably put an EQ boost at 500 and a cut at 4K. I can't see it, but I'm guessing that's 4K. Yeah, 4K. So this transfer function is showing us what we did inside this processor. Let's look at another one. Everyone clear with this? Do you have any questions so far with transfer function? You know what an FFT is now, and you know how transfer function divides two FFTs, which is why we always need a reference, and then only we can take a measurement because it's relative. And all these, this is relative amplitude, relative phase, and impulse response shows you relative time. Let's look at the same loudspeaker. What happened? We see a little LF elevation. We know there's an LF elevation. How can you elevate LF? Why do you think LF would have elevated? Sorry? Yeah, subwoofer. Somebody went and decided to add a couple of subwoofers there. Or, any other way? EQ? Yeah? Somebody decided to go all crazy on the EQ and push low frequencies. Or maybe there were subwoofers, but there were two, and then somebody made it 4. So you're seeing an elevation. So you're changing the ratio of subs, you're adding subwoofers, or you can see this kind of a change because of equalization. And we don't know what's happening here because we don't see the processor. We'll come to that. Now let's look at impulse response. Impulse response window is showing us relative amplitude. Note how I use the word relative every time, because this is relative, because it depends. When the source, the input FFT changes, your result will change, because everything is compared to that. So you have relative amplitude in your vertical axis, and you have relative time in your horizontal axis. What we can also see here is if it comes closer to 0, your impulse response, that means your output is lower in level than your input. Then you will see a number between 1 and 0, less than 1 and 0. If it goes up, if it's more than 1, that means your FFT output is more in level than your FFT input. What it will also tell you is polarity. Was this information that we were able to get using an RTA? No, but now we know. If it goes out in the positive, if you see an impulse in the positive side of amplitude, you know it is polarity normal in relation to input. If it goes down into the negative, you know that whatever you're measuring is out of polarity, not phase. Polarity and phase are different. I wish I could do that now, but no, we'll not get into that. So if it goes down into the negative, you know it's out of polarity. So this is something that already makes this tool so much more powerful than an RTA. Now, in time, if you're coming left of your center, that means your output is coming earlier than your input. If you're seeing an impulse to the right, you know your output is coming that much later than this. So you're getting relative time information here. Now let's look at a real life impulse response. We were seeing very ideal ones because those are all done in the electronic domain. If you come out to the acoustic domain, you will see something like this. We're seeing, let me go back. Sorry. Just when you think everything is working, stops. Yeah, so what do we see here? Let's analyze what we see here. We see two impulses in this impulse response window. One is higher in amplitude than the other. One is earlier than the other. So this is first, and this comes in a little later. What this could mean is this is direct sound, which means this is the sound that is coming straight from there. It could mean we're only contemplating, we don't know for sure. This could be a reflection of a wall somewhere, or it could be a asynchronous signal from another loudspeaker which is far away. Yeah, maybe you've put the mic here and this is closer, you're getting this is direct, but this is also playing at the same time. So you'll see a second impulse a little later. This is how you know whether your measurements are how good they're going to be eventually, just from the impulse response window. Now, let's look at relative phase. This is the phase window that you would see in a transfer function. You're seeing phase, which goes from 0 to plus 180 and 0 to minus 180. Is that how we've learned phase? How does phase go? Does it go from 0 to plus 180 and 0 to minus 180? Is that how you were taught? It's 360. What's happening here? So this is just a way of showing that 360. Otherwise, I'd need an endlessly high screen to see my phase response going from 0 to 360 through to 720 and then so on. So we're just wrapping it. So every time it reaches 180, it starts again at the bottom and then goes up, again starts at the bottom and then goes up. Now, this is a phase response that we've taken. What we can tell by just looking at this screen is that we have a part of the signal coming in early. We see another part of the signal that is in sync. And we see a part of the signal that is lagging. So that is coming earlier than the input FFT. This is coming perfectly in sync. This is coming in later. So that means the FFTs here, the offset was not synchronized. Something is off. And phase, as we all know, the relationship changes. You might have, what was the time period of 100 hertz signal? 10 milliseconds. So if I have my input and output FFT offset by 5 milliseconds, my 100 hertz wave is 180 degrees out of phase, correct? Is that correct? Half cycle. But what happens to my 1 kilohertz, which has a time period of 1 millisecond? So in 100 hertz, I'm 180 degrees phase different. But by the time I go to 1K, I'm 5 cycles behind. So this is why you see different. Yeah, it's not like how you would imagine time and signal. When it comes to phase, it is dependent on the frequency because the time periods are so different. This is the wraparound I was talking about. So if we had an infinitely high screen, this line would have actually continued from here and gone up. But to make it all fit on this little Mac screen that Apple makes for me, we have to do this. Yeah? So instead of going all the way up, it again comes down, starts from here, and once it reaches that 180 again, it'll flip, come back down and start again. It's just a different way of looking at this screen. We spoke about this, how phase, can you see the change in how phase is changing as you go higher in frequency? Here, at 1K, at 500, we're 180 out. Correct? That means this is that 500? Yeah, at 500. But as you go higher in frequency, this changes, this relationship changes. I'm not going to get into the details there, but if any of you are really interested, I'm going to be hanging around here and we can have a chat about it. And if you have something to share, yes, we could definitely do that. So from this screen, I can tell that this is a 1 millisecond delay because my first phase wrap is starting at 1 kilohertz. That means I have a time offset of 1 millisecond. So I can actually just look at this screen and tell a lot about the signal that's happening in terms of time. Let's do the same thing. What is the time offset do you think you have on the pink line? Is that pink? Yeah. What is the time offset do you think you have on the pink line? Do we have any time offset? What did we say about flat lines? Identical signals. No time offset. What about the orange line? Where is the first phase wrap happening? No? 500 is the shift. When you see a vertically straight line, that is only the depiction of the graph because it's not changing with time. Yeah? What is the first wrap that is changing with time? 1K. That means this signal has an offset of 1 millisecond. What about the orange one? No, sorry, the green one. I'm crazily close to the screen. What about the green one? Where is the first phase wrap? Is it here? Is it here? 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 How many of you say it's here? Yeah, so this is roughly about 10 kilohertz. What do you think the time offset is? Easiest way to get time period, divide 1 by the frequency. How much do you get? 0.1. So we know the first phase, if the first phase wrap is at 10K, you calculate time period and you know your time offset. Now, what this window will also tell us is polarity information. Where else did we see polarity information? Impulse response. If it was in the positive cycle, all good, friends. If it goes into the negative cycle, negative side of the relative amplitude, they were out. We have a similar situation here. If everything is at 0, we know everything is good. No time offset, no polarity reversal. If we see something at 180 out of phase, we all know our polarity is 180 degrees out. So in your phase response window, you should see, if you see a line like this, you know things are not in phase. Now, phase shift. How many of you, we've all heard people saying, oh, don't do too much EQ, it's going to mess with your phase. Yeah? Have you ever tried seeing how much it messes with your phase? Let's see. All we did here is put a low pass filter at 1K. This would have been a perfectly flat line. But now because of that, just because of this 1K low pass here, we're seeing this. This, again, remember, is a part of this. It just, you join it and you get that. Does this happen only with low pass filters? No. It also happens with high-pass filters. Similar situation. Let's see what this relationship is. In this case, we have 3 filters. One is doing a boost, a wide bandwidth boost. One is doing a wide bandwidth cut. We have 4. We have 2 doing narrow. They all have the same gain. Can you see that? It's all 15. This is the gain difference. So it's either plus 15 or minus 15. So all 4 filters have the same cut or boost. Let's take the orange line. Is the orange line a wide bandwidth EQ or a narrow bandwidth EQ? Wide, because it's taking out a lot of frequencies along with it. Let's look at the orange line here. It's a very shallow slope in phase. Correct? Let's look at the blue one, which is the same plus 15, but it's got a very narrow bandwidth. What happens to the phase here? The slope is much steeper, much harder in change, but it's also changing a lot lesser of your whole thing. It's not going full width. So phase relationship does not change with gain. If you have the same gain, you will have the same phase shift. If you have wider bandwidth, you will have shallower phase change. If you have smaller, tighter bandwidths, you will have a more steeper phase change. If you add signal, like we're doing in the orange line, plus 15, your phase shift will look like a sine wave in a positive cycle. Starts in the positive cycle and goes down in the negative. You do the opposite happens in phase. So you cut, your phase response goes in like a negative sine wave. Yeah, so that is a lot of information that this window is giving us. Now, when it comes to transfer functions, this is one of the most important things. All these examples that you saw on screen a lot of them were taken in electronic domain. So you don't see a lot of variation and everything is nice, what's coming in is coming out and there's nothing getting added, removed or anything like that. Coherence is coherence is the signal to noise ratio between your input FFT and your output FFT. Does everyone know what signal to noise ratio is? Yes. So what happens if you have bad signal to noise ratio? What happens? Noise. You hear as much noise as signal you're hearing. So do we need good signal to noise ratio or do we need bad signal to noise ratio? We need good. We need higher. The higher, the better. So there is a line that shows how coherent our measurements are. There is a line that is showing us this signal to noise ratio across frequencies. Can you see that little red line running up there? This is the coherence line. You will see a similar line in different FFTs. We're using the SIM3 here. All these examples are from SIM3 captures. So, but every FFT software will have very, very similar things that you can use. So you have frequency, as always, in the horizontal axis, and you have coherence. So it's showing you coherence per frequency. And this ranges, in this case, from 0 to 100%. It's not dB, it's percent. It's just telling you that relationship, and that the closer to 100 you are, the better your readings are. Now let's talk about a few factors that affect coherence. Why do we need to know these factors? Do we need to know coherence? Yeah, we need, because we're trying to achieve the best coherence possible. And in order to do that, you need to know how to achieve that best possible thing. So if you look at this, does the coherence look good? It looks good for a part of it, but a part of it, no. And what part of it looks good? I think I'm really close, I can't see, but let me try to follow this line. I think it ends somewhere here-ish, yeah? And then you start seeing ripples that keep increasing. You would see this if you haven't set your time offset. You again have that 1 millisecond, 1K relationship, yeah? So that means there is a time offset of 1 millisecond, which is why at 1K you start seeing this these funny things. Because until then, that 1K is fine. It doesn't larger wavelengths, time period, yeah? So time offset is one of the main factors. And this is one of the factors that is human error. So it's also one of the most common ones. Because the machine does everything else fine. But if you forget to go and check your time offset and set it, you'd see something like this. And if you see very defined chunks, you know that is because of time offset. What about this? Good coherence? No. It's good for a part of it, but the other part is not great. What do you think is the cause here? Could this be time offset? Does anyone think it could be time offset? Why not? Time offset will incrementally degrade your coherence towards the HF because your time periods are getting shorter and shorter and shorter, and they're more affected because of the time offset. But in low frequencies, no, this is something else. This is not time offset. Let's see what this is. So I have my signal, which is my input, which is the signal that I'm getting from the loudspeaker. But I have noise in the room, and there's a lot of noise in the low frequency region. So my noise is corrupting my signal when I'm trying to take the measurement, which is why this is happening. Because when it comes down here, the transfer function is not able to tell whether this noise is part of the original signal. It knows it's not part of the original signal, but it's not able to separate the measured channel to give you a good measurement. How can you tackle this? What do you think is the best way to fix this? Let's say it's a loudspeaker with a microphone in a room at Palm. What is the best way you can tackle this situation? Think about signal to noise ratio. How can you change that relationship? Sorry? Yeah, that's a very good point. Turn the level up of the loudspeaker. So your signal is louder now. Or, sorry? Yeah, take the microphone closer. So your direct signal is now louder than the noise that is around you. Yeah, those are two ways you can deal with it. I'm glad people are listening. I can't see you because I keep looking at this and it's all dark once I turn back around. Yeah, so we're all good with coherence. Similar situation here again. That could, if not noise, you could have a lot of reflections. Reflections are another factor that will really corrupt your FFT measurement. And can we increase the speaker level to change signal to noise ratio in this case? Why? Because the reflections are linked with that. So you keep turning up your loudspeaker, and your reflections keep getting louder along with it, so you're not helping yourself. There's only one way to tackle this. Sorry? Yeah, take the mics closer. So now you have a better direct signal versus a softer reflected. So just to show you comb filter, you could see something like this in phase. Comb filter, we've all heard comb filter. That is because it actually looks like a comb. And this is happening because we have two impulses, all with very similar amplitude, with a time offset. And it's starting somewhere here, 500, yeah? That means we probably have a time offset of that magic number 1 millisecond again, yeah? So we learned a few things. Let's put it together now to look at an overview of the system. This is where the triple channel transfer function comes into picture. Most transfer functions are one channel, one transfer function, which is two signals, your input and your output. Triple channel transfer function is something that was introduced by Meyer Sound and the SIM back in the mid-80s. And we're doing this. We're measuring the input, which is coming from the console. We're doing an FFT here. We're taking the output of the processor. So whatever change you make in the processor, you're seeing here on the red line, we're doing a second FFT here, and we're measuring the room using a microphone. The green line, we're doing a third FFT here. So we can constantly compare these two, or these two, or these three. I mean these two. So we have 3 transfer functions that we can do, and this gives us a lot of information about our system. Let's see what we can do. I didn't make any change in my processor, so now I know my processor is good. My room looks realistic. This is what I'd probably do in the room. And the result is the third one, which is microphone versus console. So this is what is coming from the FOH desk or whatever you have that is your source, and this is what your microphone is saying. So this is the overall system. What does the system include? It includes your processor, your loudspeaker, your room. So this is the final. This is what we typically see when we do an FFT. Yeah, we're taking a reference source, which we're feeding the processor and speaker and everything, and we're taking an output. But we add this. And there is a way in SIM to overlay these two. We'll see that later. So you can see all the information in one place. Now, let's move on. There are some things that are important before you start doing any transfer function measurements. The most important thing is to level match everything. Gain structure. We all know what a gain structure is? Yeah? So it's good to have good gain structure across all your measurements. You can't have, it's not good to have -20, 0 here, and -40 here. Because then your amplitude, what amplitude is transfer function showing us? Is it showing us absolute amplitude? No, it's showing relative. So if you go off on your gain structures here, that relative amplitude is going to be all over the place. As in, you're going to see lines at different places, and you can't really put them together. This is the second step. Once you have your levels in place, time offset. Go to your impulse response window, set the time offset, make sure both the signals snap, and then continue with your measurements. If you don't do your time offset, we already know that things are going to go crazy. You can see that time offset not set here in the coherence, and see what happens to your phase. If I just go and do a delay compensation here and set the time offset, that same signal looks like this. Yep. Any questions so far? No? Good to move on. Remember I said we can overlay things because we're doing triple channel transfer function, and you can see everything in one window. Spot the differences. Have you played that in the newspaper? What do we see in the second one that is different from the first one? Yeah, you're seeing a blue line here, which is changing. That is the processor measurement. That means we've put in an EQ here, which is boosted around 100 hertz, I think, 150. Yeah, and you'll see that result here in the measurement of the speaker. So, moving on. Phase. I can't see. Okay, phase. So, we've measured 2 loudspeakers separately. Can everyone see the yellow and the purple or pink line? Yeah, purple line. The yellow, do you think it's is the loudspeaker top or the subwoofer? Top, yeah, because it's going all the way into the high frequencies. And your purple line is subwoofer. So we take a measurement of the top speaker. We save that trace. And then, before we save the trace, we make sure we have our gain structure in place. We make sure we have our delay offset in place. Everything is good. Save the trace. And then we go and measure the subwoofer. And it would start with looking like this. Yeah, the subwoofer is not aligned here. I'll tell you how we go to get that. We start measuring the subwoofer. You'll see it separated because of a time offset. Then we don't change the delay offset for the subwoofer. We leave the delay offset that was set for the loudspeaker top because we want to match the subwoofer to that delay offset. And then we start dialing in our delay and try and match the phases at an overlapping point, which is usually close to the crossover, because those are the frequencies that are being produced by your loudspeaker top as well as your subwoofer. And as we dial in delay, you will see those two snap in and come into place, and voila, we have a aligned loudspeaker top and a subwoofer. Any questions? So phase matched, we take an overall measurement of the system, and it all looks good. Everything is in place. Phase is nicely stitched here together. This is our goal. Now, let's do some real-life measurements. We had a little bit of glitch with networking today, as things always are. Not everything is supposed to work on a given day. So I'm going to move this laptop there and show you some measurements of the sim. We'll start with this. I'm going to tell you what I've done here before I start taking any measurements. I have a SIM3 hardware analyzer here, which is inside the rack. It's not a software, it's a hardware analyzer. And you're going to see the output of this on the screen in a bit when we switch around. I have a Galaxy 408 here, which is a loudspeaker processor. I have output 1 of this coming to this loudspeaker here. I have output 2 coming out into this subwoofer. So I have 2 separate outputs for my top and the sub. I am using a microphone to take measurements, which is going back into the sim. And this is what we see. Let me show you things here. Let's get rid of this. And yeah. So do these windows look familiar now? We have our, I need to go back there. Remember this? What is this? Spectrum analyzer. So showing you frequency and amplitude. We have our impulse response, which here is labeled delay finder. It is the delay finder because it's actually finding the time offset between those 2 signals. And we have our frequency response, which will also, let's start doing a measurement. I'm going to play some pink noise from this first, like we discussed. And what are the steps? Make sure your gains are fine. Make sure your step 2, delay offset. Yeah, so we said that. Let's play some pink noise. The pink noise is coming out of the sim, so the sim already has a reference because it knows what it's sending out. I'm going to have to yeah, so now everyone knows what's on the screen, right? You have your amplitude response. What is the red line? Coherence. It is the red line. You don't let things go over that. Yeah? And what is this? Phase. Yeah? So this is a transfer function that is taking an FFT input, which is the source, the pink noise coming out of the sim. In this case, the sim actually does a really nice thing when we're using Meyer sound products. It has something called a sim bus. So it's internally doing all the routing for the sources. So I can just go to the Galaxy processor and say, okay, this is my source now, and this is my processor, and it automatically picks the signals. So yeah, does anyone have a question with this window? Because we need to clear that now, otherwise the rest of it is not going to make sense. Everyone on the same page? Yeah? Okay, good. So I took a measurement of my loudspeaker top. Have I done everything that I needed to do? Not yet. We got our gains in place here. I don't know if you at the back can see, but there are VU meters here that are showing me gains coming off my reference. That is the input FFT, the output FFT. I can see my microphone here. Triple channel transfer function, so I'm seeing 3 things here. Now I'm going to do this measurement again, and I'm going to go and do the important thing, that is delay offset. Because without that, the delay offset here is already done because I was playing around, but let me show you what happens if that is not set. I'm going to go and make this. Let's change that. I'm going to play the noise. Pause that. I'm going to save this trace. Let's say store. I'm going to say speaker top. I'm going to store that. I'm going to bring that here. I'm going to take it off for now. And let's take a measurement of the subwoofer. Another thing with doing measurements, I've noticed the signal doesn't have to be very loud. If you have a ratio of about 20 dB is 15 to 20 dB is safe. You don't have to blast pink noise to make measurements. Can you really hear the subwoofer? No, but it's just enough to do the measurements. So you don't have to go blasting pink noise through the venue to get your signals. Check what your background noise is. So let's do this actually. Can you see my, I don't know if all of you can see, but the bottom VU meter is actually showing the SPL here in the room right now. And if I keep quiet, it's close to 70 dB. Yeah, and I'm going to play this noise of the subwoofer. I've got 80 dB, so I've got 10 dB difference, and that is enough to do the measurements. So let's go and start this again. I did not go and change time offset. Time offset is still what it was when it was this loudspeaker. Let's go and do this measurement again. So that is the amplitude response in the top window of the subwoofer. As you can see, it's band limited to low frequencies. That is the phase response of the subwoofer. I'm not seeing any phase information higher up here. Why? Because there's nothing coming there. Yeah. So let's go and turn that loudspeaker top trace that we brought. Are they matched? What is that overlapping range between these two speakers? 100-ish. Can you see a phase offset here? Yeah? You can tell how much this phase offset is by looking at this window. Let's pick one frequency. Let's say this red line. Maybe 100-ish. Yeah? The loudspeaker top is at 180? Let's say, just for this. And the blue line, which is a subwoofer, at that same frequency is how much? 110? Yeah? I can't see from here, you'll have to tell me. About 100, 110, yeah? So that means we have a phase offset of how much? 180, 110? 70. So we have a 70-degree phase offset here. Now, what I can do is start dialing in. And because that slope, can you see there's a difference in slope? Is that visible? This slope is steeper. This slope is shallower. Thank you, Chris. This is steeper and this is shallow. That means this signal is coming in late. So let's go and dial in some delay. And I'm going to leave that thing running on the screen and let's see what happens. Can we switch to, I want to show you what I'm doing in the Galaxy so you know there's no trickery here. I'm going to ask my friend there to swap to my laptop screen so I can show you what I have here. Okay, let's pull that over. Yeah, so my, remember I was talking how SIM does that internal routing using the SIM bus? Yeah, I can just go and pick console, processor. I can pick my input FFT and other reference points within the processor itself. But here, we have output 1, which is the subwoofer top. We have output 2, which is the loudspeaker top. We have output 2, which is going into the subwoofer. Do you see any delay here? No. And all our levels are good, everything is good. I'm going to go and dial in, let's say, 3 milliseconds on the subwoofer. Yeah? Let's go and say 3, enter. And if we go back to the sim, how many of you think the phase response of the subwoofer is going to change? Yeah? Let's go back to the sim screen. Closer. Yeah? It's come closer, but is it? How many of you think the delay is fine? How many of you think it's less? How many of you think it's more? Remember that key, the slope. Has it changed? Is it gone beyond what was earlier? Let's try a little lesser delay time. I'm not going to switch screens back and forth, but you will have to trust me that I'm telling you the truth. Can we quickly go back to that screen? Since we switched anyway, let's say 2.9. And I'm going to pull the screen back so that we don't have to switch. We can go back to the sim screen. Should we try 2 milliseconds? Just to see what happens. Shifted. Let's try. Can everyone see the change? It's closer to what it was now. Let's try 2.8. Too much. Can you see that difference? I wanted to show you how it's moving down. Let's do 2 milliseconds. I think that's good. Yeah? That's pretty good. They're both snapped. So that means now the overlapping frequencies between this and this are in phase. Yeah? Now, let us close this. I'm getting confused between which mouse to use now. I'm going to take this off. I'm going to store this. I'm going to say sub. I'm going to save that. And let's turn the live trace off. Yeah? So the green line is a subwoofer top, and the yellow line, I keep saying subwoofer top. The green line is a speaker top, and the yellow line is a subwoofer. We see phase all good, and amplitude response looks like this. Now, until now, we were taking the measurements separately, correct? Now let's do a measurement together. I'm going to turn these traces off. I'm going to turn that on. I'm going to turn the speaker top on. I'm going to pause. I'd say that's pretty good. Can you see there's no cancellation, there's no drop in amplitude at where the crossover is stitching in? That's another way of telling that you've done your alignment right. If I didn't do this right here, you'd see a drop in level. Now I don't have a drop. I have all looking good. What could this be? Sorry? Does this somehow look related to this? It does, right? Wherever you're seeing drop in coherence, you're seeing drop in level. What could that be? Reflection. Most probably a reflection coming off maybe one of these walls. And that reflection is corrupting the signal here and showing you a drop, but you know it's a drop because it's a reflection. Yeah, so don't look at one window, don't look at one line. Look at the whole picture. You need to look for three things. You need to look for amplitude, you need to look for frequency, and you need to look for phase or time. Yeah? So any questions? I think I'm done. I have a couple of minutes maybe if you have questions, or we're out of time and we'll hand it over to someone else. Are we good? No questions? I either did a good job or a really bad one. I'm assuming I've done a decent job because you don't have questions and you all look like you understood what's on the screen now. Well, thank you so much for coming. I really appreciate your time.
I wanted to ask you, when we have a subwoofer out taken from console, subwoofer out wherein we are running our line arrays or tops full range, and then we are having subwoofer outs.
Yeah.
So then what is the point where we match the phase? Because usually there are 2 points where they cross over each other acoustically.
Yes. That's a very good question. The question is very short, but the answer is super, super long. But in short, there is no way of aligning the phase in one place and expecting that to work throughout the venue, because there is a geometric offset between your flown array, which is maybe 8 meters, 10 meters in the air, and you usually have a ground subwoofers on the ground. So for let's imagine the loudspeaker top is there and the subwoofers on the ground here. And if I'm standing here, I am maybe 2 meters from the subwoofer, but because it's a triangle and this is the hypotenuse, this is maybe 2.5 meters away from me. But as I keep moving away from there, this relationship is going to change. Yeah? This distance will change, and this distance will change. And the delta, or the difference between these two lengths, the relationship will keep changing. So there is, in short, there is no fixed way of, there is no way you can align in one place and expect it to work throughout.
So then where is
the solution to this would be is to try and bring the subwoofers and the tops as close together as possible, which is why flown arrays are done very often.
But then usually where is the place in the venue where we should align it?
It really depends. It really depends. Some people like to align it at the FOH. Some people like to align it either in front or behind the FOH. If you'd ask me, just a personal preference, I don't prefer to do it at the FOH because then it's summing at the FOH and you have a low frequency build-up at the FOH, but your audience is probably not hearing the same thing. So I'd say a little ahead or a little behind, depending on the size of the venue and the size of the rig that you've deployed there. But there is no one answer. But yeah, it's a really, really good question that you asked there. Any more questions?